Hello everyone, this is continuation of our last lecture on electrostatics where we dealt the electric charge and field in the first part of it. This is the start of next part of electrostatics, which is electric potential and capacitance. Before moving ahead, I would like to say that we got very good response for our first series on electrostatics, and hence we are moving ahead and will be making more series and will be solving more numericals in the coming slides. And I personally don't check all the comments and things, but I do get an idea about the comments you paste and things like that. This whole channel which we started is managed by one of my colleague, Ronak Mishra. But yeah, whenever you get any query, any feedback, you do post in the comment. I'll surely get an information from them. Yeah, thanks. Let's start on the topic. So the topic is electric potential and capacitance, right? So let's start only with electric potential first. Electric potential energy. Right. So, what exactly is potential energy, first of all, right? First of all, what is potential energy? You might have come across this term potential energy in your old junior standards, right? That the energy by virtue of size or position and things like that, they are nothing but potential energy, right? So, when we talk about potential energy, we talk about work done, right? In general, whenever we talk about energy, we talk about work done, right? Okay, let's say there are let's start with gravitation just to give you a basic background, right? Let's say this is some height, right? This is some height and this is my surface level, this is ground, and this is some height, right? And you have an object of mass m, right? You have an object of mass m, right? So now you need to place this object at a height h, right? At a height h. If you have to do that, you need to do certain work, right? And this work is happening against gravity, right? So after you are able to put this object to this particular height, how much amount of work you did? So the gravity which is oppressing your work is what? Mg, right? Mg is the gravitational force, and distance through which you moved it is h. So this is the net potential energy, or let's not call it potential energy. This is the work done by any force which is able to move this particular object mass m from ground level to a height h, right? This is the work done, right? And this work done, since it was against the gravity, this is a negative. So this minus mgh is the work which is to be done to place this body at a height h. And where this does this work go? This work gets stored as the gravitational potential energy, and now this particular body has a potential energy, right? So that's what is gravitational potential energy, right? Okay, so work and energy, it goes hand in hand, right? Whenever you do some work, it gets stored as some energy, right? So now let's think in terms of charges, how it applies in terms of charges, right? Okay. Right, so we just understood the concept of gravitational potential energy. This was just to give a background of what potential energy is and how energy is possessed by any body, right? Now let's talk about electric or electrostatic potential energy, right? Let's say whenever you talk about electrostatic, we have a system of charges, right? So let's say there is a charge body which has charge plus q1, right? And then there is again a charge body plus q2, right? Clear? So there is a force in between these two, right? What is that force? That force is electrostatic force, right? Which is given by what? K q1 q2 by r square, if this is r, right? Now this is a stable system, right? This is a stable system which has no motion and things like that, right? But let's say if you have to move this particular charge, right, from this particular point r to, let's say, some more distance. Now let's say this is the new point where q2 has to be shifted, and let's say this is x. So you need to shift q2 by a distance x, right? So as I said, that q2 has a force coming from q1, right? Q2 has a force coming from q1, and you have to shift q2 by certain distance, right? So you need to overcome that force. Either you need to take the support of that force, or either you need to overcome that force, because electrostatic force can be either repulsive or attractive, right? Clear? Okay. Now let's say one more scenario, right? Let's say in other scenario, this q2 is at a distance r, right? Now you need to bring this q2 to close to q1, right? And let's say this is x, right? So now the work you are doing is against what q1 is exerting, because q1 was exerting a repulsive force which was in this right direction, and you need to bring this charge towards q1, which means you need to do some work to do that, right? So that work is nothing but potential energy, right? That work is stored as potential energy, right? Let's see how potential energy is defined, right? Okay. So potential energy is nothing but it is work to be done to bring a system of charge together, right? Work to be done to bring a system of charge together, right? Okay. Let's say there is a charge plus q1, right? There is a charge plus q1, right? And then at a distance r1, there is a charge plus q2, right? At a distance r1, there is a charge plus q2, right? Now you need to bring this charge q2 to a new distance, let's say r2. This is the, let's say, new distance in which this q2 is to be brought, right? So here we are doing work against this q1, right? Now let's find out what is the amount of work we are doing, then we will be able to appreciate what potential energy is, right? Okay. So what is force exerted? Let's say force exerted between q1 and q2 is what? K q1 q2 by x square, right? X is my variable which basically tells me the distance from between q1 and q2. X is that variable, right? So force between q1 and q2 is what? K q1 q2 by x square, right? Now what do we need to find? We need to find the work done, right? So work done is nothing but, you know, work done is force into displacement. Clear? So this is k q1 q2 by x square into dx. Clear? Now what is the net work done, right? What is the net work done? So for net work done, I need to integrate this and this also. So initially I was at R1, finally I'm at R2, right? So now let's find out what is the work. K Q1 Q2, and this is nothing but minus 1 by x from R1 to R2, right? So this is nothing but K Q1 Q2 which is nothing but K Q1 Q2 1 by R1 minus 1 by R2, right? This is my work done, right? And this, since this work done is against the force, the potential energy will which will be generated or stored, which it will be the negative of work done, right? So this u, which is representation of potential energy, is nothing but minus of w, which is nothing but k q1 q2 1 by r2 minus 1 by r1, right? So this system has a potential energy of k q1 q2 1 by r1 minus 1 by r2 minus 1 by r1, right? So to shift q2 from a place R1 to a place where it is at R2 distance from Q1, unit, this is much amount of potential energy is stored in the system, right? Okay. Now let's define what exactly is potential energy, right? Let's define. So potential energy is defined as work done in bringing a charge from an infinity point to a fixed point, right? Let's explain diagrammatically, right? Let's say there is a charge plus q1, right? It has field all around, right? It has field all around. So if I'm bringing a charge q2 from, let's say, one point of reference is infinity, from infinity to a distance r from this q1, the amount which I am working, the amount of work I am doing here is being stored as the potential energy in this system, right? Okay. So my new first distance is infinity, or and the final distance is r, right? Okay. So let's calculate how much is the value, right? So force exerted between q1 and q2 is nothing but, this is electrostatic force is nothing but k q1 q2 by x square, right? Okay. So work done is nothing but, work done by electrostatic force will be Fa into dx, right? So nothing but k q1 q2 by x square into dx from infinity to r, right? Now if you solve this particular integration, you will get minus k q1 q2 by r, right? So this is work done by electrostatic force, and since we are applying an external force to bring charge against this electrostatic force, so this net energy which I need to apply is negative of this work, which is k q1 q2 by r, and this is stored as potential energy in this system, right? So potential energy of this system is nothing but k q1 q2 by r, right? Clear? Okay. So let's explain again. Let me explain again from the beginning. So potential energy, electrostatic potential energy is defined by work done by an external force in bringing a external charge from infinity to a fixed point is nothing but potential energy, right? So here, this is my fixed charge and I'm bringing q2 from a point infinity to a point r, and I'm applying external force to do that, to overcome this electrostatic force, and this much amount of potential energy is being stored in this system, which is k q1 q2 by r, right? Okay. Right. So let's say there are two charges q1 q2, the distance is r, so net potential energy is nothing but k q1 q2 by r, right? Potential energy, since it is an energy, you know the unit of energy is nothing but joule. SI unit will be joule. Clear? The quantity, it is a scalar quantity. Do remember that electric field intensity was a vector quantity, but electric potential energy is a scalar quantity, right? And you can also find the dimension. What is dimension of energy? It is nothing but ml square t minus 2, right? Okay. Okay, now let's talk about a term called electric potential, right? Electric potential. Electric potential. Right. So we just defined electric potential energy, right? So if we have a charge plus q1, the work done to bring this charge plus q2 in its vicinity from infinity to a fixed point r is stored as potential energy, which is k q1 q2 by r, right? So electric potential is nothing but work done in bringing a test charge from infinity to a fixed point, right? We explained in electric field, when we are dealing with electric field intensity, what is a test charge? A test charge is a plus unity charge, plus 1 coulomb is the test charge. So now we have specified q2 as nothing but plus 1 coulomb, right? So what will be the new potential energy, right? K q1 by r, right? So this is nothing but v, which is electric potential. This is nothing but electric potential and represented by v, right? Clear? So electric potential is also called as potential energy per unit charge, right? Potential energy per unit test charge, right? Okay. What is the unit for electric potential? It is volt per coulomb. I'm sorry, this is nothing. This is joule per coulomb, not volt per coulomb. This is joule per coulomb, right? We will not talk about volt and all that, but this is nothing but joule per coulomb, right? Joule per coulomb, right? Okay. Right. So let's talk about potential due to a point charge, right? So potential due to a point charge. Point charge. We just discussed briefly what exactly is electric potential, right? So it is nothing but work done in bringing a unit positive charge from infinity to a fixed point, right? So let's say this point charge is plus q, and in the vicinity of plus q, at a point p, which is at a distance r, I need to find what is the potential at this particular point, right? So I can easily find it by placing what? Placing a unit positive charge r, and then I'll be able to find it, right? Okay. But if I place a charge plus q, let's say this plus q is the charge, right? So this plus q is the charge at point P. So what is potential energy of this system? This is nothing but kqqq by r. This is kqqq by r, right? To find potential, potential is nothing but potential energy per unit charge, right? Or either I can place a unit positive charge. It's as same as this. This is nothing but kq by r, right? So potential energy potential due to this q plus q at point P is nothing but kq by r. Clear? This is kq by r, and the unit is nothing but joule per coulomb, or this is also called as volt. So you can use any of the units. So potential is kq by r, right? Now let's go back and think about electric field, right? Let's go back and think about electric field. We discuss electric field in a similar way. Potential at point P is nothing but kq by r. But if I talk about electric field, that was nothing but kq by r square. Kq by r square, right? Okay. So now, if graphically, if I need to put, right, if graphically if I need to put this E or V versus R, you see E is proportional to 1 by R square, right? But V is proportional to 1 by R. So how graphically it will look like, right? So let's say I have a point, this point is, let's say, 1 meter, right? And there are two spaces here, which is the distance greater than 1 is the on the right side, less than 1 and greater than 0 is on the left side, right? So if I talk about the distances which is greater than 1, since electric field is varying to square of the distance, it will be always at the bottom hand, and potential will be always at the top of the graph, right? Because potential will be always greater than electric field if I take other things as constant, right? So how graph will looks like? So graph will look like this. Let me draw it with a different marker. Okay, so this is my electric field. Let's say this is my electric field. So my potential will be something like this, right? So which one is potential, which one is electric field? So this is my electric field, this is my potential, right? Clear? Okay, right. So we discussed electric field also due to system of dipoles along the axial and equatorial lines, right? So now is the time where we will discuss the electric potential due to a system of dipole, right? So this is the system of dipole. Dipole is nothing but equal and opposite nature of charges separated by some distance. So you see plus q and minus q separated by distance 2a, and at a point P, which is at a distance r from midpoint of this dipole, and it is inclined to an angle theta, we need to find the potential, right? Okay, so let's say the distance from minus q to p is r1, from plus q to p is r2, right? So analytically, if I calculate the potential, let's say these 2 points are a and b. So due to potential at p due to a will be what? kq by r2. Simple direct formula. Potential at p due to b will be what? Minus kq by r1, right? Net potential, if I need to find, it is nothing but, so potential is a scalar quantity. I'll directly do the scalar addition. This is nothing but kq 1 by r2 minus 1 by r1. Clear? Now we need to find what is r2 by r2 and r1 in terms of r theta a, right? And then we can find what is the net potential, right? Clear? So given quantities, to us are, if I talk about this, if I talk about distance, a is 2a is the distance between charges, right? R and theta is the position where we need to find the potential. So we need to find R2 and R1 also in terms of these three quantity to proceed with the final answer, right? So let's try to calculate, right? Let's think about R1, right? Let's think about R1. So if I draw a perpendicular here, So this triangle, if you see, let's say this is X. So PXB is nothing but a right angle triangle where R1 is the hypotenuse of that. So this distance, this net distance will be what? This is nothing but R cos theta. And this perpendicular is nothing but R sin theta, right? So this small distance, if I see, this is nothing but R cos theta minus A, right? So if I need to find R1, which is hypotenuse of this triangle, it is nothing but R cos theta minus A whole square plus R sin theta whole square. Clear? Now let's solve this, right? So this is nothing but R square plus A square minus 2RA cos theta. This is R1, right? So we found what is R1. Let's find what is R2. So R2 is nothing but it is R. Similarly, it will be R square plus A square plus 2RA cos theta. Right? Clear? Okay. Now, let's try to simplify this, right? So if I take R1, right? Let's ignore R2 for some time. If I take R1, right? It is, if I take R square common from here, what is R1? I think this is nothing but R1 square. We are calculating the h square, hypotenuse square. That's the formula. So if I take R1 square common, this is nothing but A square by R square. And this is nothing but 2A by R cos theta. Clear? This is 1 plus A square by R square plus 2A by R cos theta, right? Generally, we say that the distance where we are calculating the field, which is very, very greater than the distance between the charges of dipole, right? So this term will be negligible. This A square by R square term will get negligible. So what is R1 now? R1 square is nothing but R square into 1 minus 2A by R cos theta. R1 square is nothing but 1 R square 1 minus 2A by R cos theta, right? Okay, let's simplify this a bit more. Now if I calculate R1, R1 is nothing but R will come like that, because it's if I remove the squares, and this 1 minus 2A by cos theta, I'll get under root 1 by 2, right? Now I found R1, right? I found a simplified version of R1, but can I use this directly in this equation? This is my final equation. This is my final equation. Can I use this directly in that equation? No, right? I need 1 by R1, reciprocal of R1, right? So what is reciprocal of R1? It is nothing but 1 by R into 1 minus 2A by R cos theta, and the power is minus 1 by 2. Clear? The power is minus 1 by 2, right? Now this, we need to solve this particular expression now, and this is a binomial expression, right? This is a binomial expression. So if I try to solve it, if for a general binomial expression, 1 plus x to the power m, let's say this is a general binomial expression where it says 1 plus x to the power m and x is less than 1. So this is nothing but this can directly be approximated to 1 plus mx. This can directly be approximated to 1 plus mx. So I can just bring this power as a coefficient of x and I can place it, right? So now let's find this R1, right? So now R1 is nothing but 1 by R1 is 1 by R 1 minus, I'll bring this power here. So minus 1 by 2 into 2A by R cos theta. So binomial, how it comes, we will discuss in mathematics later on. So this is nothing but 1 plus A by R cos theta. Clear? This is 1 by R1 is equal to 1 by R 1 plus A by R cos theta. Clear? So similarly, 1 by R2 will be what? This will be 1 by R 1 minus A by R cos theta. Right? Clear? Now I found what is my 1 by R1, what is my 1 by R2, right? Now can I place these two values in this particular expression of potential, right? Let's do that. So this Vp, potential at P, equal to KQ 1 by R2 is 1 minus a by r cos theta, and 1 by r1 is minus of 1 minus a by r cos theta. So this is nothing but kq into 2 by r 2a by r cos theta. So if I rearrange it, this is kq 2a cos theta by r, right? This is nothing but k q 2a cos theta by r, right? Right. So Vp, if I rearrange it, it is k q 2a cos theta by r, right? I think we miss this 1 by r. So this will come somewhere here, kq by r, kq by r. This is r into r. So this q into 2 is nothing but dipole moment, right? Kp cos theta by r square. So what is my potential here? Potential due to a dipole at a point P is nothing but Kp cos theta by r square. This is general formula. Now I can find it for axial point as well, equatorial point as well, or for any angle I can find the potential now. Right. So let me write the formula properly again. So let's say this is a system of dipole, charge plus q and minus q, and the distance between them is 2a. I am finding at a distance r from midpoint and angle theta at a point P. If I need to find the potential will be given by Kp cos theta by r square, where P is the dipole moment, which is q into 2a, right? Okay. So so let's try to find it for equatorial position. So equatorial position will come somewhere over here. So theta equal to 0, right? Sorry, axial position, not equatorial. So for axial position, where theta will be equal to 0, my potential will be what? It will be Kp cos 0 by r square, which means Kp by r square, right? For equatorial position, equatorial means perpendicular to this, orthogonal to this, where theta will become nothing but 90 degree. So my potential will be 0 because cos 0 is 0. So at equatorial position, the potential is 0, right? Clear? Okay. And also do note that potential due to dipole is inversely proportional to square of the distance where we are calculating it, and not the linear. It is the square power. When we calculated for a point charge, it was varying to the power 1, right? It was inversely proportional to r, but for a dipole it is inversely proportional to r square, right? Okay. Now the next topic is relation between the electric field intensity and electric potential, right? So relation between, can I directly write it, E and V? E is nothing but electric field intensity and V is the electric potential or electrostatic potential, right? So let's say there is a charge placed in uniform electric field E, right? And net potential of that system is V, right? What is the force acting on that charge, right? If E is the electric field, force is nothing but Q into E. Force is magnitude of charge into electric field, right? What is the work done by this force in moving this charge? The work done by this force will be nothing but force into displacement, right? Work done by this force will be nothing but force into displacement, as simple as that, right? Okay. Now this work done, we said that the potential energy is the negative of work done, right? Potential energy is negative of work done. So if I need to find du, it is nothing but minus of dw, which is nothing but minus of qe dr, right? Okay. So this is the integration of qe in with respect to dr, right? Okay. Now what is electric potential, right? If I take q here in the denominator, this is nothing but integration of edr, and this whole term is my electric potential. So dv is minus of integration dr, right? dv is equal to minus of integration of dr. So integration of electric field intensity with respect to position vector gives me the potential, change in potential, right? You can see this work has nothing but dot product, so this is all dot, right? Integration of edr, dv equal to minus of integration of edr. And if I need to find e, this is nothing but minus of dv by dr, So electric field intensity is differential of potential with respect to position vector, with respect to position, right? And field is nothing but integral of electric field intensity over position, right? Okay, so this is what is relation between electric field intensity and potential, right? So we just discuss v is nothing but it is integration of e into dr, negation of integration of e dr, and electric field is nothing but differential of v with respect to d with a negative sign. Now with this we can say that these two are of anti nature to each other, right? So you see, in a direction of increasing potential, the electric field will be negative, right? We can say that, right? And if potential is constant, so you know the differentiation of constant is zero, electric field will be zero, right? So now with this you can also say, we discussed that inside any conductor, right? Inside any conductor, the electric field is always zero. So we can also say that this conductor has equal potential around all its surface, right? So we'll discuss these equipotential surfaces in our next lecture on electric potential and capacitance. And till next time, thank you.